There are very many things in the classroom situation which is not quite obvious. One of the things is why x to the power of 0 is equal to 1. We say that in any number raised to the power of 0 is equal to 1. It seems so confusing, because when we say x to the power of 0 is equal to 1, there is that kind of a 0 as well as 1 on the right side. And also intrinsically we know that whenever one thing gets in kind of a power, x to the power of 1, x square, x3, x2, etc., etc., the exponential it just grows. But how is that? When x to the power of it has the exponent 0, it is equal to 1. Of course, in a classroom situation, we try to prove that we put x to the power of m divided by x to the power of n. Then we make it x to the power of m minus n. Then we make it m equal to n, etc., etc. But it is not at all convincing. Can we just try through experiment through paper? Yes, we can. It's obvious how x to the power of 0 is equal to 1. We shall start with a small paper like this. So this is one full paper which appears to be a rectangle. So let us fold it once edge to edge. So like this. So we have folded only once. What has happened? There is a straight line here, and also it divides the complete rectangle into two equal parts. That means the two equal parts we have with one fold. Let us try to fold it again. So second time we have folded. Open it and see. It has got 1, 2, 3, 4 parts. We shall continue. So fold it for the third time. So when we see, there are 8 parts. Shall we continue like this 100 times, let us say? Obviously, you say that in this small paper cannot be folded 100 times. But that's the beauty of mathematics. What we cannot do, by holding the paper like this, we can definitely, calculate what happens when it is folded. Even a small paper like this is folded 100 times. So for that, one particular and peculiar thing, of characteristic of mathematics, comes into our existence. That is the pattern. So what is the kind of a pattern? What exactly, remember, what exactly we have done? How did we start the experiment? We took a paper, we folded it once, and we observed it divided twice. Again, you fold it second time, it divided the area into 4 times. Again, for the third time we did, it divided into 8 times. So let us take a paper and try to tabulate, what exactly we have done. This tabulating is not peculiar to mathematics. You go to a kirana shop, you buy so many items. He also makes a table. The number of items you have got, the price what you paid, he makes a table. So table is only a tool. So that particular tool, which is not particular to mathematics, we shall use. So let us remember what is countable here. We did through this paper, number of times we folded, began to count the number of divisions it made. So let us say, so number of times folded. That means this paper is folded how many times? So what exactly we counted? Number of divisions it made. Number of divisions it made. So first time you folded, one time, yes, we got 2 divisions, that is 2. Second time you folded 2, we got 4 divisions, 4. Third time we folded, we got 8 divisions. Like this, if you were to hold it for 4th time, you will get double this, 16 times. I also asked you, if 100 times it is folded, how much it is? Of course, 100 times it cannot be folded. But I told you, in mathematics, we can do calculations and exactly tell you, if at all, you were to hold it for 100 times, how many divisions you get. So what we are trying to do is see the pattern here. The first observation you get is all these are even numbers. Next, the second observation is these are all multiples of 2. We can write them, like this. 2 into 2 into 2 into 2, etc., etc. So observe here. If it is 1, it is 2. If it is 2, 2 times 2. If it is 3, it is 3 times 2. If it is 4, 4 times 2, 2, 2 is multiplied. So now you get the clue through this pattern. If it has to be in 100 times, it is definitely 2 into 2 into 2 into etc., 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 100 times. This we say is the pattern. So now comes the mathematical language. Can we convert it into mathematical language? Because mathematics has a language. So we can also write it like this. It is 2 to the power of 1. It is 2 square. It is 2 cube. It is 2 to the power of 4. Definitely in the same pattern, it is 2 to the power of 100. That's how, in the mathematical language, we write this. A man who doesn't know, let us say, the mathematical language, how he will read this? He will say big 2, small 100. But if you know the mathematical language, you say it is 2 to the power of 100. Next, there is another characteristic in mathematics. We always generalize. N times instead of 100, if you are to put n, what happens? Definitely it is 2 to the power of n. Now you see this one. This has become a formula. How we got this formula 2 to the power of n? By holding the small paper. Now, I draw your attention to the difficulty of mathematics also. When you see this formula 2 to the power of n, it is not at all visible that we started with a paper. What we did, an experiment. How we got it? It is not at all visible. This is abstract. We got this formula. Then you have to add something. How we got this formula? That means to say this formula was invented by holding the paper. For the purpose of counting how many times you have folded, how many divisions you made. This is the difficulty in mathematics. We say that mathematical formulae like this are abstract, because unless you investigate in what the context it was made, you will not understand. So now, this formula we have got. This has got beautiful advantages. For example, we have put n. We can also put n plus 1. That means to say, if it is 100 times you have folded, the number of divisions you got is 2 to the power of 100. We can put n 1 lakh, then it will be 2 to the power of 1 lakh. So definitely it will show you the exact number of divisions you get when you hold it 1 lakh times. That means we can also generalize. Accuracy is a characteristic of a formula. So this is the advantage of mathematics. Once you know the pattern, you can make out a formula and extend it to whatever the number you want. Now reverse the process. This reversing the process is also specifically a characteristic of mathematics. So n you have put, it is 2 to the power of n. 100 you have put, it is 2 to the power of 100. 4 times if you have to hold, it is 2 to the power of 4. Again 2 to the power of 3. Like this 2 to the power of 2. So one time you have folded, you got 2 to the power of 1. Let us say the same paper, the small paper, you did not hold at all. That means to say n becomes 0. That means it is 2 to the power of 0. You did not hold it. So how many divisions you have got when you did not hold? It's only 1, isn't it? That means if you hold it once, it becomes 2 times. If you hold it 2 times, it becomes 4. If you did not hold anything, n is equal to 0, that is 2 to the power of 0, which contains only 1 division. So that's why 2 to the power of 0 is equal to 1. Again I told you, this kind of a generalization for n we have made. In the similar way, we can also generalize for any kind of a number. Let us say if you were to do it for 3 times, let us say once, twice. This is the 3 times holding. 1, this is the second time, 3 times holding. So even if you were to hold it for 3 times at every stage, when you did not hold it at all, it is 3 to the power of 0. You have got only 1 division. That's why we can generalize exactly x to the power of 0 is equal to 1. So what we started was a small paper. We started experimenting it and found a beautiful illustration through the experiment of holding that x to the power of 0 is equal to 1.